Avaz. So, hi everyone. It's Newton and Nelson here. So, today we are going to be covering chapter 2 of Ruby under the microscope. And this is a new book we started last week, and it's what we'll be looking at for the coming months, I think, or the coming couple weeks. So, Nelson, I was going to share my screen, and then
Okay, go ahead.
yeah. So I don't know if you can see it very well.
Yeah,
Yeah. So
yeah,
like
it's great.
okay. So last week we looked at basically what we are trying to see in chapter 1 and chapter 2 and chapter 3, which we'll cover next week, is we are trying to see how Ruby executes your code. And basically what we are looking at here is if you write, let's say something like put 2 plus 2 and you save it inside a file with the file extension .rb, and then you run that file or you run that script. How does Ruby execute the code inside that file to give you the output, which will be 4 in your interpreter, for example, like IRB? So last week we looked at tokenization, which is one of the steps, and then we looked at parsing, and then today we are going to be looking at another one of the steps during execution of your code, which is compilation. And the chapter starts off by defining the word compile. And it states that the word compile means to translate your code from one programming language to another. And what we are looking at here is that now let's say I've written my code in a Ruby and I pass it through a compiler. What is basically going to happen is that I want to change that Ruby code from Ruby into a language that is understandable by the compiler. In this case, machine language, which is usually the kind of language that is understandable by the compiler that is related to the programming language you're using. So when you compile a C program, the compiler translates the C code into machine language, a language that your computer's microprocessor hardware understands. And this is the same for Java, for example, which is another programming language, whereby you're going to have the Java virtual machine transforming your Java code into Java bytecode. And that is the key takeaway here. To compile is to translate code from one programming language, in this case, the programming language you've written your program in, depending on if it's Ruby or if it's Java or if it's C, into another language, usually referred to as machine language, that is easily understandable by your computer. So moving on to that, this is our roadmap. We'll be looking at the differences between a Ruby 1.8 and Ruby 1.9 and so on. And then we'll look at how Ruby compiles a simple script. In addition to that, we'll see the difference between how Ruby compiles a simple script and how Ruby works with blocks and how it compiles those blocks. And then we'll look at displaying YAV instructions and other concepts like local table and how to work with the various kinds of arguments that you can have as associated with method calls. So in Ruby 1.8, there was no compiler. And usually what happened is that when you write your Ruby code, that code is tokenized and then it's parsed. So at the end, you're going to end up with an AST node. And that AST node is a concept we looked at in chapter 1. So when you have that AST node is going to be looped through by Ruby's interpreter, and that used to be, I think Maths's Ruby interpreter, MRI, and MRI would go through that AST step by step, executing the code one node at a time. And this is when you contrast this to Ruby 1.9 and 2.0, which had the introduction of a compiler. And here the compiler is named yet another Ruby virtual machine, or YAV. So what YAV does, or I think that the main purpose of introducing this compiler was due to purposes of improving the speed of Ruby programs. And what we see here is that with the introduction of the compiler, you have an extra step that your code has to go through before it is executed. And here, as you can see on my screen, when you have your Ruby code, it will be tokenized, it will be passed, so it will be turned into AST nodes, and then those AST nodes will then be turned into YAV instructions individually. So for each of those AST nodes in the AST tree, each of those nodes will be converted into its own set of YAV instructions, and then the YAV compiler will then go through each of those instructions and execute your code as per those instructions. So that is the key contrast we are looking at here. Prior to Ruby 1.8, we didn't have a compiler, and therefore we didn't have that extra step of turning the AST tree into YAV instructions. And then following the release of Ruby 1.9 and 2.0, and I think the subsequent newer versions of Ruby, you had the introduction of that compiler, yet another Ruby virtual machine, and therefore that introduction of that extra step, which is the conversion of every node which is part of your AST tree into its own set of YAV instructions, which instructions are then converted into know which instructions are then evaluated by the virtual machine. So a few things to note between, like I said at the start, Java has its own virtual machine as well, which is its own compiler. And one of the differences between yet another Ruby virtual machine, which is used by Ruby 1.9 and so on, and the Java virtual machine is the fact that, first and foremost, in Ruby, you're not going to have to manually compile the code yourself. So the compiler or the yet another Ruby virtual machine will be running in the background, as opposed to what you do in Java, whereby you have to manually compile the code yourself. So that is one of the differences. Another difference is that Ruby never compiles your code all the way to machine language. And as you can see in figure 2.2, Ruby interprets the bytecode instructions. The Java virtual machine, on the other hand, can compile some of the bytecode instructions all the way into machine language using its hotspot or just-in-time compiler. So what this means is that, referencing figure 2.2 or 2.2, you can see that we are ending at this step of the YAV instructions as opposed to going all the way into bytecode. So these YAV instructions are the ones that will be evaluated and interpreted by the virtual machine, as opposed to us relying on bytecode like we see in Java. So those are the two distinctions between the two.
Um,
Yeah.
just pause right there.
Okay.
I think
Okay.
I think we need to clarify the difference between bytecode and machine code. Because I think they're getting mixed up a little bit here. Um, so can you tell me what machine code is?
Um, Machine code. I thought the two terms were interchangeable when I was going through the text, or at least.
They're not quite interchangeable. I mean, there's a real difference between them.
Okay.
Um, so um, the when Java was introduced, it introduced this term called bytecode. And it was and when Java when you turn your text into bytecode, what Java is doing, it's compiling your text to something that can run inside of the Java virtual machine. That bytecode is in binary. It's, it's ones and zeros, right? Um, and similarly, machine code is also in binary. It's ones and zeros. Almost everything in your machine is ones and zeros. But the difference is that the ones and zeros of the bytecode can't be sent directly to the processor. In other words, um, the the processor does understand certain ones and zeros as, okay, this is an add instruction, or this other set of ones and zeros is a move instruction. And the processor has a whole set of these things that it knows how to do: push and pop and add um, and multiply and different instructions that are the basic operations that the processor knows how to do. Um, the problem is that depending on your processor, like a 16-bit Intel processor, will have different instructions than a 32-bit Intel processor. And it will have different instructions than the 64-bit Intel processor. And the machine code that you generate for one of those processors will only work on that processor. The promise with Java was that you can uh, compile your code, the text that you wrote. You can compile it to bytecode, and that bytecode can be run on 32-bit hardware and 64-bit hardware, and you can run it on Intel machines, and you can run it on ARM machines, right? Like it runs on your phone as well. So the purpose of Java and the purpose of compiling it to this bytecode is that once you compile it to the bytecode, the only thing you have to swap out is the virtual machine. So the Java virtual machine is the thing that understands the Java bytecode and says, okay, what are the instructions I want to run? Okay, this is the set of instructions I want to run. Okay, what processor do I have? Okay, I have this processor. So in this processor, I have to give it this set of machine codes versus this other processor that has a different set of machine codes. And so the Java virtual machine is there to sort of be an intermediary between the bytecode and the actual instructions that the processor can run. So bytecode by itself, without a virtual machine, cannot be understood by the processor. If you give the processor some compiled uh, Java bytecode, it's not going to know what to do with it. It's going to say, "Well, I don't understand this set of ones and zeros. This does not map to an add instruction or a move instruction or anything that I'm familiar with." Does that sort of clear up some of the difference?
Yeah, what I'm getting is that we have the virtual machine acting as like an intermediary between the byte code and then what the processor can understand.
Yeah,
Okay.
yeah, that's completely correct. And
Yeah.
then since this book is a little bit old, This diagram that we're looking at here, where it says Ruby and then tokens, and then the abstract syntax tree nodes, and then the YARV instructions. It's now, as of Ruby 3.1, and Ruby 3.1 was released in, I looked it up. It's December 25th of 2021. Um, there's this other thing called a YJIT.
Yeah, yeah, just in time.
Yeah, and it's a
Mm.
just-in-time compiler for Ruby. And so that YJIT will when you um, load the file, it will compile um, the instructions in that file into um, into something that the Ruby virtual machine can understand.
Okay.
And
So
those will be run in YARV. So
mm.
YARV is still used, but it's the YJIT is compiling things for YARV.
I have two questions.
Hmm.
First and foremost, when you look at this diagram, the diagram on page 32 at the very bottom,
Yeah.
the author references this part and he says, "Code the Ruby core team writes." I suppose in this case, which is Ruby, this because this diagram is meant to illustrate what happens in Ruby 1.8, right?
Yeah.
So I assume that when he says code the Ruby core team writes, this is supposed to refer to Maths' interpreter.
Yes. Yeah. Um,
Yeah.
it it's when you type in your terminal, when you type in the word Ruby, that word Ruby is um, is written in C actually, and that C produces machine language. So that C interpreter takes the Ruby code or whatever and translates it into machine language for your processor.
Okay. So when I contrast that with now this diagram on page 34, right?
Hmm.
When he talks about code the Ruby core team writes, this time around he's referring to the virtual machine. Oh yeah.
Yeah, it's all part of Ruby. It's all part of that Ruby command.
Okay. So um I think another question I have is that you've talked about YJIT, and now in this book we've seen YAV, and then in Ruby 1.8 there was Maths' interpreter. My question is, what is the aim of of coming up with all these virtual machines? Even in like the last chapter of Eloquent Ruby, he listed like so many, like all different kinds of virtual machines, and I think just-in-time compilers. What is the aim? Is it like to increase the speed? Like when you run a Ruby program, I don't get that.
Yeah, well, start reading the second paragraph.
Yes?
Look at the page you're on there.
Oh,
The
oh yeah,
primary reason for using YARV is speed. Uh,
yeah,
yeah, because the instead of like what we saw is that we had to do a whole lot of work to turn, because at the end of the day, the code you write is just a text file, right? That's all it
yeah.
is. It's just a text file. And a text file is very, very difficult to process. You had to go through a tokenizer, and we saw how many steps that took. Every character, you have to go in and say, okay, this is a character, this is a period, this is a space. And then once you find a whole word, okay, now that's a token, and I can send that token to off to be processed, right? So it's actually a lot of work to try to turn your text into an abstract syntax tree. And instead of doing all of that work every single time that you want to run your program, instead we just do it once. And in Ruby 1.8, it was stopping at creating the AST nodes because it would create those AST nodes uh, and then every time that it had to do some work, it would interpret the entire abstract syntax tree. But we saw like the abstract syntax tree is um, is a big uh, tree structure with a lot of entries that have to be parsed every time, right? So
Yeah.
instead of parsing the entire tree every single time you want to do some instruction, well, let's instead in Ruby 1.9 start to compile those instructions and so we don't have to reinterpret the tree. We just know all the instructions that need to be run.
Okay. So yeah, that clarifies my question. And then I think we'll proceed to the next subsection. So how Ruby compiles a simple script, and in this part we are just going to be looking at basically how YAV works in a bit more detail, and we'll be using this example of a simple Ruby script that calculates the value of 2 plus 2 being 4. So inside this Ruby file, I suppose it's a Ruby file, we write put 2 plus 2, and we expect the output to be 4 because when you add 2 plus 2, you get 4. So here is the AST tree for that Ruby script, the one we've mentioned of put 2 plus 2. And when you look at this tree, at the very top, you have node scope, and then you have a function call. In addition to that, you have a node call, and then you have a node literal. A node literal could mean like an integer. In this case, for example, 2 is a node literal. And then when you look at a node call, this refers to a method. Remember when for the ones that went through eloquent Ruby with us, plus or the plus operator is a method in Ruby, and that is why you see that here it's referred to as method ID plus. It's a method. And when you look at put 2 plus 2, if you were to add brackets to it, you'd see that this 2, the very last 2, is the argument to the plus method, and the very first 2 is the receiver of the message which is associated with the plus method. So for the f call, which is the function call, here we see that the method referred to as put is a function call. And what does this mean? This means that when you call put, you've not explicitly specified a receiver of that message, and that is why it is referred to as a function call, while the plus method is referred to as a node call or an actual method call. Because when you look at put 2 plus 2, you can see that you have an explicit receiver which is specified for the plus method, and that is 2, as well as an argument that is passed inside the bracket, which is 2 as well. When you contrast that with the call to put, you can see that we just call put. And at that point, we are just trying to assume that the current self will be the receiver of this message, which is put. And that is kind of a subtle difference between the two. So you have a function call that is put, you have a method call, which is plus, and then you have a receiver. Like I've told you, a node literal is just could be an integer. Now, for example, like in this case, you have a receiver which is 2, the very first 2, and then you have an argument which is 2, the very last 2. So YAV is a kind of virtual machine that is referred to as a stack-oriented virtual machine. This means that when YAV executes your code, it maintains a stack of values, mainly arguments and return values for the YAV instructions. So what this statement means is that at, at every point, you're going to have values being pushed onto the stack, as and these values may be receiver values. They could be arguments that are pushed onto the stack. And then after those values are pushed onto the stack, you're going to have method calls being performed for those receivers and while passing in those arguments. And then after evaluating those method calls, you're going to have a result now returned to you. And that result, or the result value, is also left on the stack trace. No, sorry, on the stack. And that value is what will be returned to you in the end. So in the example of put 2 plus 2, you're going to push, and this is something we're going to look at in the following pages. You push 2 onto the stack, and the very first 2 is the receiver. You'll also push 2, which is the argument for the plus method, onto the stack. You'll evaluate what 2 plus 2 is by calling the plus method on the very first 2, which is the receiver, passing in the last 2 as the argument. And the result of that operation is going to be left on that stack. And it is what will be passed in as the argument to now the puts. So you'll have puts, eventually having puts, and if I was to include the brackets, you'll have puts, open brackets 4, because 4 is the value of 2 plus 2, and that is why you'll have the 4 returned to you. So that is why it's called a stack-oriented virtual machine. You have things being put onto a stack, methods being called, and then the value being left onto the stack, after which that value is returned to you. So I think I'll go through this step by step. In order to compile the put 2 plus 2 AST structure into YAV instructions, Ruby will iterate over the tree recursively from top down, which means we are going to start from node scope, and each AST node is converted into its own set of YAV instructions. And node scope tells the Ruby compiler that it's starting to compile a new scope or section of Ruby code, which in this case is a whole new program. So the interesting part is this part of the function call, where we are going to have YAV instructions generated that will be equal to put self. And in this case, self will be the, let me just read from here. In figure 2.5, the Ruby compiler first creates a YAV instruction called put self to indicate that the function call uses the current value of self, the current value of the self pointer, as the receiver. Because remember, I talked about this puts method call as not having specified an explicit receiver. So we'll have to figure out what that receiver will be of that puts method call. And here it states that when you call puts from the top level scope, that is the top section of this simple script, self is set to point to the top self object. And the top self object is an instance of the object class that is automatically created when Ruby starts up. One purpose of top self is to serve as the receiver for function calls like this one in the top level scope. And what this means is that a scope in which you've not explicitly specified the receiver for a given method call. So you have a note here, which I think is a bit important. In Ruby, all functions are actually methods.
Are you still there? You abruptly cut out.
Yes?
Sorry, are you still there?
Yeah.
Okay.
Eh,
Oh no. Your sharing stopped. Um, I see he's coming back. Are you back?
Yeah, so I don't remember why had I stopped.
Okay. Can you share your screen again? We have 8 minutes.
I'm just going to breeze through this section. Where had I stopped?
Yeah. So we were just getting started with the details of the compilation. Oh, did you crash again?
Hello.
Yeah, you crashed again.
Yeah. I don't know if
So
you can
you
hear
were
me
you were
now.
just getting started with the details of the compilation steps. Um,
The
Let me try
the
to
the
find the
reason
page
was
number.
I don't know if you can see my screen.
Yeah, now I can.
Yeah. So I think I'd reached this point of explaining why it's called a stack oriented virtual machine.
Yeah. So
Yeah.
you'd
So
gone
we
to
have
page 36, I think.
yeah. So I'm going to use this figure 2.6 to summarize. Remember, I talked about put self,
Hmm.
whereby we've specified what self is for the put method call. Remember, we hadn't explicitly specified what the receiver is. So self will be the top level scope. And then in addition to that, now we'll see the whole stack-based virtual machine in action here. We put an object 2 onto the stack, and then we put another object 2 onto the stack. And the very first two is the receiver, the second two is the argument. And then we send the message, in this case, the plus. And as you can see here, method ID plus, because we are dealing with the plus method. So we'll send that message to the receiver, which is the very first two, passing in one argument, as you can see, argc1, with that argument being 2. So finally, following that, we'll have the last step being a replacement of these two sends, the send the send which involves the plus method call and the send which involves the puts method call. They'll be replaced by opt plus and opt send simple, which are specialized dev instructions and are meant for optimization. And what opt plus and opt send simple are, these are basically, like, I could say, specialized instructions for common operations. For example, in this case, the addition operation, which is 2 plus 2, that's represented by opt plus. And then opt send simple is what will be associated with the puts method call. Yeah, I think that summarizes that part.
Yeah.
So I don't know, Nelson, if you have something to say.
No, you're
Bef-
explaining this great. You're actually it's clarifying some things for me as well because I went through it quickly and this detail is helping me cement some things in my head.
Yeah. So the next part is the one relating to compiling a call to a block. And this is still another example we saw in part one. But I think we should start a new meeting for this.
Okay. I'll stop the
Yeah.
recording here and then we'll move on.
Okay.